about I was thinking that because this reading group, we are going to read a paper, but not read a paper in the traditional sense. It's going to be I've created a bunch of slides for you, and I'll go through the slides, and you guys can stop me and ask questions anytime. And then we will go through some code, and then you can ask me questions on the code. But like I'll what I can do is I can show you the code and not go through it, because if you guys are interested in theory, then it's much more easy. So raise your hands if you want me to go through the code. Otherwise, drop your hand. Okay. Okay. So I think everybody wants me to go through the code. Okay, I'll skim through it, but basically I have created a repository for you guys so that you can go there and play with the code. And I'll try to keep it updated over time. And what the plan is that uh, I had 5 sessions planned. So the 5 algorithms I was planning was: number one today, DQN; number two, A3C; number three, PPO, DDPG; and then uh, number four was PPO, and number five was C51. So I'm planning to do these 5 algorithms one at a time, but so that you can participate, I'm thinking that like it's better that you guys know some torch as well, PyTorch. So what I can do is I can skip one week, like next week I can skip that. I can insert another session and make it 6 sessions. So the second session would be PyTorch, and then later on we'll cover the rest of the sessions as planned. So who thinks that is a good idea? Like, should I do a PyTorch session as well? And then we should um, like go forward, or do you want me to just go to the papers and give you the code and you can try it on your own? Like, should I do a PyTorch session or not? Can you drop your hands all at once, and then can you drop all your hands? Yeah. Aminul, can you drop your hand? Okay, now raise your hand if you think that I should do a PyTorch session. Okay, so 4 out of 7 people think that I should do a PyTorch session. So uh, it's a majority so far. So I'll do a PyTorch session next time. So how it will work is I'll for this session today is DQN, Deep Q Learning. Oh, wait, there are two Siddharths here.
Yeah, I'm just joining from my laptop.
Okay, so there basically today will be DQN and next time will be PyTorch. I already have that prepared, so I don't need to worry too much about it, work too much about it. And then next after that we will have 5 sessions, 4 sessions. So those will be 4 algorithms. So total overall we will be having 5 more sessions apart from today. And hopefully everything goes according to plan and I'm able to give you the code and explain to you what these ideas are. Okay, so let's start with today's discussion. I anticipate it will be like 1 hour, and if you guys have questions, just stop and raise your hand anytime. You can drop your hand if you want. um, and if I don't see your hand, just interrupt me, don't worry about it. Okay, great. So I'll share my screen. Okay, can you guys see my screen?
Yeah, we can see it.
Okay, I'm not sure I can maximize it. Okay. So I'll not maximize it. Is the font like readable?
Looks good to me.
Okay. So today we are discussing deep Q networks. which started with this paper in 2013, in which they showed some results, good results on these games, a game suit called Atari, in which there were like 50 or something games, I think. And the link is here. I'm not going to read through the paper. I'm going to show you the paper. Like I have the paper here. Uh, I'll show you what I'm talking about, and then you guys can read it on your own. And if you have any questions, you can ask me. But this is mostly a presentation based off this so that I can understand things from first principles. So, what this is saying is that in general, uh, reinforcement learning it has a um, there's challenges in reinforcement learning, and that uh, there are new technologies in deep learning at that time, 2013. There are new technologies in deep learning which are helping to break through things in computer vision, speech recognition, but there are more challenges from reinforcement learning perspective. This I've covered in the slides. So it shows basically how you can use a neural network, which just takes in the input, the image as the input, the image of the game emulator as the input, and then plays the game. It can play the game using an algorithm. So that is what we're discussing today. And basically it's a game. These are games of Atari 2600 games. These are I don't think there are 2600 games in it, but these were like popular games in 80s and 90s, if I remember correctly. And then basically they consider what the background is, that what's MDPs are, uh, what returns mean. I'll discuss what this is. What is the Bellman equation? I'll tell you what that is. What is the training function for the neural network, and how they do the gradient update. This is not needed because PyTorch automatically handles gradients for you. You don't need to worry about it. You just need to give it a loss function, and it will take care of the gradients. And then what are the related work that has been done? It shows that in the past, TD Gammon, which played backgammon, and there were these games and their applications of chess and Go and checkers. These games are played using some programs, but TD Gammon is the most popular one because it uses a similar technique as used in this paper, which is TD method. TD means temporal difference. What temporal difference means will not be clear today, but I'll explain it eventually. Um, and then it talks about what the problem in training is, like the networks diverge. When I was creating the code for this session, I had the same problem. It was diverging, but eventually I got one uh, possible hyperparameter setting that worked, and you guys can play with it. And eventually we will realize that we should use some kind of a double learning technique to improve it. But double learning means you have two networks, and you take one network and you copy over the network over some time, and that's how you learn the network. Like it slowly changes over time. One network slowly changes over time. One network changes faster over time, and you keep the two networks and you keep training them over time. So that's the double learning, and in general, that is a good approach to learning. We'll see that soon. Like I'm not going to discuss it today, but we'll discuss it if somebody asks, and it will be in one of the future implementations. Then it discusses what the other methods are, what the neural fitted Q learning is. Uh, it's another approach. So these are just approaches before 2013, like these approaches were popular. And then it tells you about the 2600 emulator. It's a game emulator. Um, and it was shown as a reinforcement learning platform by DeepMind, people in DeepMind. And then they discuss deep reinforcement learning. So they talk about this experience buffers. What did they do? Like the two contributions from this paper are that they have an experience replay, which is something that solves the problem of correlated samples. I'll discuss what that is in the slides. And the second approach is that second thing is that they have this thing called sorry, they have this algorithm, right? So I'll discuss that as well in the slides. But in general, they're discussing here about experience replay and what does it mean by online learning and Q learning. And there's something called as uh, off policy and on policy learning, but you don't need to learn it today. But I'll, if anybody asks, I will tell them the question answer. um, and then pre-processing and model architecture. Now here they're discussing about what the image size is. Like they're having 210 to 160 pixels and they're converting it to 184 cross 84 image. That's what the homework is for today. Actually, I'll discuss it. And then experiments wise, they've done experiments on 7 games: Beam Rider, Breakout, Enduro, Pong, Qbert, Sequest, and Space Invaders. So out of this, you may not know some of these games because these are old games. But Breakout is like DX Ball, in which there's a I'll actually I'll show you some examples. Space Invaders. Let's Space Invaders. So this is a Space Invaders one. So you can see, like, can you see the game being played? Yeah, Jackie or anyone
Yeah,
can.
yeah,
Yeah, yeah. So this is the game of Space Invaders. That's one of the games in the suit. Then there is Pong. Pong you already know. So it's think which one is it? I mean, the gameplay is similar, but the semantics or the graphics differ. But basically, the gameplay is like, yeah, you have this kind of a game. You have to take the ball and move it over to the side. But this one is bad. And Space Invaders. These two are the most important ones, I think, for now. And then there is a card pull game which we are going to which I'm going to show you today. Card pull is this game where you have a card and a pole, and what you can do is you have to move the cart left or right. So there are only two actions you can do: left or go right. And what you have to do is you have to balance the pole. If the pole starts upright, and if you don't move properly, then the pole will start falling, right? So if it goes like within 25 within 15 degrees of either side, then the game is over. And I have a failed example and videos of that as well. So I'll show you both of them at the end again. Okay. So in the paper, then they discuss the experiments, what optimizer they use, what is frame skipping, how to help training. I'm not gonna discuss all of this. I'm just gonna start the conversation today by discussing what Q learning is and what deep Q learning is, and then eventually over time, like I'll have like these prizes over time, so that you guys can also contribute and do things. But it's not a compulsory thing. It's up to you. If you're passionate about it, do it. If you like and think it's cool, you should do it. And if you have any questions, I can answer. But like, even I am not like the best person to ask everything. I'll admit, even I don't know how to get parameters working for some games. So but I'll try my best. And one like we'll see over time that it's a cool field. You will not be bored because there's always a game to play. Okay, so any questions on this paper so far? You can unmute yourself and ask. I'll wait for like a minute, and then I'll go to the slides. So any questions on this paper so far, because we're gonna move to the slides. If anyone read it before and they thought that there was something they didn't understand, just ask me. Now it's fine, because like there's concepts here which I would talk about, but if there is something still that is lingering on your mind at this point in time, then let me know. Okay, so you know what? I can't see. So let me just see. Yeah, I can't see Zoom anymore. So I can't see if you guys are raising hands. Anyways, I'll continue because nobody unmuted themselves. So now we'll go to the slides. So in general, this is the layout that I'm thinking. Like it's not too much. It looks too much, but it's not too much. Yeah, or you might know some concepts already, like what is supervised learning, what is deep learning. Um, these concepts you may not know. I'll talk about them. Then these concepts are from the paper. I'll tell you about them, and these are the experiments. So, and there's a homework prize of 25 gift card of $25. And the way the gift card works is that if nobody claims it, like we'll go over 1 week, and if there is somebody who puts in some effort or puts in the most effort, will get the gift card. And if nobody, I think, is putting in the proper effort, then this will accumulate over time, and then the next gift card will be $50, and we'll accumulate gift cards in sessions of two. So there's no gift card for PyTorch, but there will be gift card for the next algorithm, and so there will be $50 gift card total for the first two sessions if nobody claims it this time, and then there were $50 in the third and fourth session, and the last session is a hard one, so I'll give you $50 in gift card there as well. So total prices are 150 because of 5 sessions, and for 25, 25, and 25, 25, and 50. So that's how the structure is. So if anyone has any questions regarding that, they can ask me now. Otherwise, I'll proceed. Okay. So in general, what is supervised learning? In supervised learning, I'll start with introduction, then I'll go to reinforcement learning, then I go to deep Q learning, and then I discuss experiments. So guys, can you see my cursor here,
Yeah.
Jackie? Okay,
Yep.
good. So um, first, I'll start with introduction and supervised learning. So what is supervised learning in general? What in supervised learning, you have some examples, and you have some labels, right? So for example, there's a data set given like this, where there are some images: ships, dogs, deers, birds. There's some examples here, right? And no two ship images look the same, but there's approximately similar, and you can discern, a human can discern whether or not these two are ships, and whether or not this is a bird. Like it's not easy to see it, but it's mostly discernible. Like this is a horse, this is a car, this is a ship. It looks like it when you zoom it a bit, but in general, there are examples like this, and there is labels like this, and the goal of supervised learning is to learn these correlations over some data set. So it has given, you have to have a training set where you can see these correlations, and you can learn that this example is this label, and you can do this over an entire training set. And then you have to produce high accuracy over a test set or a validation set, where you don't know what the labels are, but like the labels are hidden, and the images, only the images are given. So that's supervised learning for you. There's a data set, there are n examples or something, the training set, there are n examples, and then each example is of the form, the image or the input, and the label or a category, and you have to learn how to classify things or do something similar. So it's not just classification, but classification is a simple example that for now. So just stop me anywhere if you have a question. Okay. All right. So then comes deep learning. So what is the difference between deep learning and supervised learning? Is that we have these function approximation technique. So what happens is that if you have X, an image, and you have a y, a label, and you want to create a function between them, but you don't know what the function is. Like you don't know what function will actually take this image and map it pixel by pixel to a class. So you don't know the image, but deep learning provides us this tool called deep network. Basically it's a network of matrix manipulations, and it converts a matrix of a given size to a matrix of a different size, or a tensor of a given size through a tensor of a different size. And what will happen is you can adjust the parameters of this network over time and make it learn the correct function. So this function is a function is this is a function approximator because it can approximate universally any type of function that you can give it, provided you have the correct loss function. So you have to have a good loss function. Okay, one sec. You have to have a good loss function, and if you have a good loss function, then you can learn parameters of this network properly, and then it can do any kind of task that you have in mind. So this is a function approximator, and when you have many layers of it, then it's called deep learning because you're stacking many layers deep, and this becomes a deep network. And the optimization is through gradient descent and backpropagation, and that's outside the scope of this discussion. But basically, PyTorch handles it for you. So when we discuss PyTorch, I'll show you how it does it, but you don't need to worry about it at this point in time. So all you need to know is that if there's a network and there's an input and an output, and you want to learn a function between them, from function approximation between them, then you can approximately learn a function using deep learning, and in you can use PyTorch, the Python framework, to do this kind of stuff. Okay, so people who have just entered, like if you have any questions at any point in time, just ask me. If there is something related to a previous one, then also you can stop and ask me. I'll try to answer. Okay, now we will go to what is reinforcement learning, episodic reinforcement learning. So think about it this way: there's an environment, and an agent is there who can play the episodes with the environment. So in general, it's like environment starts in a state S1, okay, and then the agent plays an action A1. So the agent cannot ask the environment how to play, but basically it has access to the environment, and it can play the game that the environment has. The environment is the game emulator. So it can basically ask it goes into an episodic flow. So this is an episode where the environment starts in S1. The agent interacts with the environment saying, this is my action. Then after it says this is action, it transitions into the next state, S2. And then the environment also tells that, oh, you did this action right or wrong, and this is a number according to it. Like if you did it right, maybe you'll get a reward of 200. If you did it wrong, maybe you'll get a reward of minus 200. So the environment is also interacting with the agent, and it gives it rewards based on what action it took in the given state. And based on the state and action, it transitions into the next state, and then the agent has a choice to take another action. And then this process continues. It gets a reward, it takes another action, gets a reward, and this goes on until a terminal state. A terminal state is when the game finishes, the game is over, and then like there is nothing to be done. So this is like a graphical version of what is happening uh, in reinforcement learning. An episode starts with the environment in some state S1. The agent acts out an action A1. For every move of the agent, the environment provides a scalar reward. A scalar reward is like a number, okay, like not a complex number, like a number. Plus 500, 3 minus 300, plus 2 minus 5, anything, 0. So it provides a scalar reward, and for every action, the transitions happen like this. There's a transition from state ST to ST plus one given action AT, and there is a distribution. Like this might be unintuitive to someone what a distribution is doing here, but basically think of it like given the state and given its action, uh, it's not necessary that it will always transition to a certain state, but it happens according to a distribution. It can transition to something else, it can transition to something else. There can be 5 states in the transition distribution, and it transitions, and the sum over all of them will be 1. So it can transition into any one of them with some probability. So that's the rough diagram of what is happening in reinforcement learning, and this is happening over episodes. So whenever it happens over episodes, it's called episodic reinforcement learning. And the episode goes like this, like we discussed. So any questions at this point in time? So just unmute yourself if you have a question. Okay. Okay. So if nobody has a question, then um, we'll discuss what the learning objectives are. In supervised learning, the objective is to minimize something, right? So in regression, it is to minimize some kind of a mean squared error or an L1 error or something, right? But in categorical in classification, where you have to distinguish between categories, it's something like categorical cross entropy loss. So there are like different objectives in supervised learning, but in reinforcement learning, the objective is a different one. It's to maximize episodic reward. So what we want is that when we play an episode by itself, like randomly play an episode, the policy of the agent, how the agent is playing the game, the actions that it's taking are such that the maximum reward is achieved in the episode. So this is like a test episode, like test examples in supervised learning. Just like that, these are test episodes. In test episodes, what we want is that the agent um, takes action such a way that the rewards are maximized. So basically, how do we capture the notion of rewards and maximization of reward? So because we know that everything is a transition, the transitions happen according to some distribution. Like this S2 is happening according to some transition distribution, S1, A1, like P of S2 given S1, A1, and so on. So we need some kind of expectation here. So the expectations are of two kinds. You can take this expectation of what is the reward you get at the first step, the reward you get at the second step, and so on until end, and that's the undiscounted reward. But you can also discount the reward when you can multiply every reward with a certain gamma. So gamma is like a number between, let's say, 0.5. So it's saying that the first reward, when I look at the episodic reward, it's looking at the first reward, then the second reward is multiplied by zero point 0.5. The third reward is multiplied by zero point 0.5 squared, and so on. So it's reducing the rewards in value over time. So it's like blurring your vision over time, right? Like this is basically you can see all the rewards, and this is like you have perfect vision. And that's the rewards you're getting. You should maximize this expectation. That's the undiscounted reward objective. And then there is a discounted reward objective in which you can look into the future, but you don't you place immediate rewards as being more important than the future rewards, and the future rewards are discounted by certain values, and these values can be adjusted. So it can be between 0 and 1 based on what you want. So in typical reinforcement learning, we keep it at 0.99, not making it 1, but in 0.99 also is a discounted case. So because you can see like at certain gamma to the power 33, let's say, uh, the discount factor will be like so small, 0.99 to the power, let's say 33, is so small that the rewards are, no matter what the size is, it just doesn't look at it. So it's like blurring the vision after a certain uh, time step. That's what the discount is doing. Okay. So, what is a policy then? A policy is how the agent acts, and there are two kinds of policies here. Like there is a deterministic policy, where you have a state S and you act out deterministically. So, given a state S, I'll only do one thing, and that is given by this function pi. And there can be stochastic policies. So given a state S, you act according to a distribution. Like you don't the policy, you can learn two kinds of policies. One is a policy which is a simple deterministic function, and there is a stochastic function in which basically the policy outputs a distribution, and you sample to according to that distribution, and then you take that action and you play out that step in that episode. So there are two kinds of policies here. And what is an optimal policy? An optimal policy is a policy which maximizes the long-term objective. So this is a long-term objective. You have to maximize for a choice of policy, for a good choice of policy. You have to maximize the rewards in any episode. So that's why there's an expectation. So ideally, yeah, I just wrote them in a hurry, but these should be capital R's because these are random variables. These are all random variables. Capital A, capital S, these should be capital R. These are random variables. This is a graphical diagram. Um, and then optive policies which maximizes a long-term reward objective. Okay, so then if we know that this is what we have to do, then how do we maximize the long-term objective? So we do it by looking at certain things and certain niceness of this distribution. Basically, when we look at this, we see a recursion happening, right? Because the R1 plus gamma R2, you can take the R2 and take it common, and you can see that there is another gamma R3 plus gamma square R4 and so on. So like there is always a there is always a hidden thing. There's a recursion hidden inside these expected reward, expected long-term objectives. So that's how we learn it. Like we uh, will show you like there's certain value functions, and based on those value functions we can learn these things. So what is a value function? So when you take like we will define certain things. So given a policy and a state and an action, the Q function is basically the reward of that state action pair plus the discounted reward. Like basically this is saying that you play out, you take the state in the state S action A, you take this in that state, you're starting with that state, you're taking the action A, and then the next action is the next state becomes Si plus 1, the next action becomes Ai plus 1, the next state becomes Si plus 2, Ai plus Ai1 plus 2, where Si plus 1 and Si plus 2 are, are given to us by the emulator or the environment, and Ai plus 1, Ai plus 2 is played according to this policy pi. So basically a q pi s comma a means that what is the value of this taking this action in this state and playing a policy. So that's what this is saying. Like if we were at this state in the beginning and we took this action, and whatever futures could happen in the future, or the expectation over time of the rewards of the episodes, that's the episodic value of a state action pair. So if there's any question you can ask at this point in time. Okay, I assume that was clear then. So visually what is happening is that you start at state S and then you take an action A and then it plays according to an episode. Like there can be a random episode because it's a random variable, like the long-term episode. And then you can take an action, you can take another action and it can lead to another episode. So the Q value is saying that across all the possible episodes from this node, what is the expected value of the reward that you get starting from SA1 till the end. And then there's something called as a value function. This is a different thing. This is a value of a state rather than a state action pair. So value of a state is like uh, well, if you have a state and you can take many actions from there, what is the best reward that you can get at that state? So Q of SA2 is the best one, let's say. So then that is the value function of S. So value function pi of S is maximized over A Q pi S of A. So take for all actions A, you take the maximum over Q values, and that gives you the value function. So with these two notions, we can define certain things, and this can give us a way to um, learn these things through deep learning. So I'll tell you how, but in general, is there any question at this point in time? Okay. So let's say that the policy that we are playing is the optimal policy. So like we said, an optimal policy is a policy which maximizes the reward. Like it's a policy uh, which is the best policy. Somehow we discovered that policy, let's say, right? So we discovered that policy, Then let's say that everything associated with it is associated with it, and like let's say that everything that's associated with it is has a star associated with it, right? Like pi star means optimal policy, q star means the q when you follow pi star s of a, and v means v star of sa is um, v star of s is basically v of pi star of s. So q star of sa, like we just saw this equation and we see that there's a recursion here. So we could replace this by q of pi star uh, si plus 1 ai plus 1, right? Because what is happening here is that there's a recursion, and what is the reward plus the gamma times the q star, and you can open this q star and it will lead to the same objective here. Because there is if you remove the gamma, if you remove one gamma, if you drop one gamma from here onwards, you'll see that it's r si plus 1 ai plus 1 plus gamma r si plus 2 ai plus 2 plus gamma squared si plus 3 ai plus 3, and so on, right? So that is essentially the expectation of that is the q function, right? So the q function from that step onwards is uh, is this thing, right? So the q star has this recursion because this recursion exists in every q pi. And then we can see that because this is the optimal policy, what is happening is that this term here is like the maximum value achievable for every possible value of ai plus 1, right? Because this is the optimal policy, and there is no other action that you can take. Like and of all the actions that you take, uh, taking this action AI plus one according to this policy pi star leads you to the best reward in the future. So it's piecewise maximum reward as well. So it's piecewise doing the best as well. So that's why you can replace it by max over all ai plus 1. And this is the Bellman equation. So what it says is that q star function is equal to the expectation over from r siai plus gamma max ai plus 1 q star si plus 1 ai plus 1, where si and ai start at s and a, and this si plus 1 is given according to the transition distribution, and this ai plus 1 is the maximum over whatever actions are possible. So how can we, like, what is this saying? This is saying is that if you have if you have a network which can output q values, right? And let's say it could output, let's say you have a discrete set of actions, like you have 5 actions, and you can forward this you can take this network, you can input the value s, and you can output the values q of s1 sa1, q of sa2, q of sa3, and so on. Then basically you can pick the best value at the end, and that is how you learned that is what this target is, right? So if you start with an with a bad policy, if you start with a bad policy, if you start with a bad q network that doesn't know anything, then over time, if you take this target network and you learn and you make this the target and you learn the value, then over time it will become the q star function. And if you run, basically what it's saying is that if you run enough time starting from a non-optimal q function, the Bellman equation will converge and produce the q star function. So if you don't understand right now, I'll explain it to you in a second. But any questions in this equation so far?
Hi,
Yeah.
what is the tau in the expected
So
value mean?
yeah, the tau means the trajectories. So I, to shorten the notation, I wrote tau, but what it means is like you can start like there are many random variables in this expectation, right? Like there is the reward, which is a random variable. Then there are more terms here: reward, a reward, reward, and there is si plus one, si plus two, and so on. So what this tau means is that this is a trajectory which starts at state S and SI AI, and then the SI plus 1 is sampled according to the transition distribution, SI plus 1 given SI comma AI, and then AI is sampled according to the policy pi star, and then SI plus 2 is sampled according to the transition distribution, AI plus 2 is given according to pi star, and so on. So that's the tau. Like tau is just a hidden notation, but what is saying is that every state is sampled according to the transition distribution, and every action is sampled according to this pi star.
Okay, thank you.
Okay. So if there is any mathematical confusion, you can ask still. Like this, don't be shy. Like it's there's not much we have covered so far, but you can see like there is a recursion, and how to use this recursion is very easy. Like I'll tell you how to use it. It's very easy to visualize. But if you have any questions on this recursion so far, I'll let me know. Okay. So if there's no confusion on this, then let's go to the algorithm. So let's say there's a big action, a big table. Like let's do this for a tabular case. What happens in a tabular case? So let's say we don't have a deep network. Let's say there's a big table in which we have the SA values, right? Let's say there's a table. So let's say there's a big table of state action values. So there's the row number is the state, the action number is the action. So let's say everything is discrete, and there is some states and there's some actions, and there's a big table of state action values, and you can put in a value at every cell. So that's a table you have. So how can we use what is the Q-learning algorithm? So for every discrete SA, we have a value in this table corresponding to QSA, and to learn the correct action value, the correct Q star SA, we can instantiate the table, let's say from 0 or something, and then we can update using the Bellman equation. And then how to use it? We basically take the environment, we play some episodes. So when we play some episodes, we have some episodes, and episodes will have state S1, A1, R1, S2, A2, R2, S3, A3, R3, and so on, right? So once we have those, we can we can update we can uh, do things like this. So consider an episode with T steps worth of data. We can have many instances of SI plus one, and AI plus one, and reward from play. Like there will be many instances of this kind of things from the play that you just did. And then for every SIAI, we can say that the value should be something that original thing plus moving towards a target little by little, right? So for a small value of alpha, uh, and this is the original value of QSIAI, and this is the target, like for SIAI plus gamma max, because this is the target from the Bellman equation. So from gamma max Q of Si plus 1, AI plus 1. So basically think of it like a dynamic programming algorithm that we're doing over a table, right? So this algorithm will convince yourself that this algorithm is essentially trying to learn the values over time, starting from some instantiation and using this just Bellman equation. That's how you would eventually update the values of the target values according to the target. So even though the queue doesn't start as a queue star, over time when you update it this way and you're moving slowly towards a target, then this becomes a q star function over time. This converges to the q star function. And like yeah, if every episode ends at a termination state, so for those you drop this part and just have the reward for the terminal state, and then reward minus the q value for whatever the original value was. So this is how you would do q learning on a table, how you would do it without a neural network. So any question in this part? What any question in what we're doing here? Okay. If not, then I'll continue. If there is, just let me know. So if we know this, then how can we use it to learn? So if we know how to do it on a table, can we do it on a function? Can we do it with a deep neural network? So the answer is yes. And how to do it? Basically, you take a Q network, a network, deep network, and then you pass it in a state, and let the values we produce be Q of SA1, Q of SA2, Q of SAN. And like there are many, like I'm assuming that there are n number of actions, but this doesn't work if there is infinite number of actions. Like sometimes there can be infinite, the action space can be infinite, right? So it doesn't work in those cases. But if the action space is finite and discrete, then we can say that, let's say we have a network which takes in the S and produces these values, and then we can have a loss criteria which is similar to q-learning, but it's basically you will have a sample. Let's say you have a sample of images from a buffer. So you sample some images from a sample some things from a buffer, and then you have k examples. So like, let's say this batch of examples B has k examples of SI AI plus SI AI SI plus 1 AI plus 1, and the corresponding reward for SI and AI. Then the loss is basically the expectation, which is approximately the 1 by k over, like it's the mean value. So it's the mean value of target minus the q value. So this is what the paper was saying, that whatever the q values are being output, so this network is outputting certain q values. What we need to do is we need to produce new q values for these, and then we can just use the ms mean squared error loss on those and update it. So what is a new value for it? It's according to the Bellman equation. It's q of s AI. The new value should be reward of SA1 plus the max of all actions from there. So and q of s dash a dash. So basically, what we have to do is we have to take the state, we have to play the actions, and then we have to play the next state. And we have the next state because we buffer, we take examples from the buffer of this form. In the from the episode, there is SI AI, and then there's SI plus 1 AI plus 1. So we already have SI plus 1 and AI SI. So all we need to do is we need to set the target to this value R of SI AI plus gamma max of Q SI plus 1 AI plus 1. So we need to do two forward passes. With this network, we need to do one forward pass with SI, when one forward pass with SI plus 1, and then we will have we will have the all the ingredients necessary for this term. We have the RSI AI because that's given us from the buffer. The QSI AI SI plus 1 AI plus 1, we do a forward pass with the input SI plus 1 and take the maximum over all the things, and then multiplied with gamma, and this is the target. And then the target minus the q, which is the original value, the original forward pass, or the original forward pass, the node corresponding to AI. That is the value that we take as the input, and that's how we get the target minus this. So we have target values for each of these, and then we just take the difference of them between them, square it, and mean it, and that's a mean squared error loss. So any question on this part, because this is the major crux of the algorithm here. This is just the Bellman equation, and this is just how we would learn a neural network. So if we don't know how neural network, we will cover it next time, but in PyTorch. But basically, any question in the algorithm here.
Wait, do we know the distribution beforehand, or
We don't.
Okay.
We don't know the distribution, but what we can do is we can play the game because we have
Mhm.
access to the emulator. So we can play the game, we can collect many episodes, and then for each episode, basically we have these kind of pairs, right? We have SI AI, SI plus 1, AI plus 1 over an episode. We have many examples of it, right?
Yeah.
So we just put it in a buffer, and that's how we learn it. Like we can put it in a buffer, we can randomly sample from that buffer, and then we can learn it using Bellman equation. Okay. Any other
Okay, yeah.
questions? Yeah. Any other questions? Okay, so we are nearing the close. This should be simple. So basically, what I'm saying is that there are two challenges that the paper says. There's two problems in learning this way. One problem is that the reward signal is sparse, noisy, and delayed. What that means is that when you play the episode, the rewards don't they are not like happening every second or every time step. They're happening like one of this will happen like 200 steps into the future. Then there will be a gap of 500 steps. Then there will be a gap of 20 steps. So it's very sparse, and because of that, what you put into the buffer is not going to be uh, easily, like it's mostly going to have the value 0. So when there's values of 0, that means that in the network, this part is 0, and then you have to rely only on this update, right? But the other problem is that the problem is that if you take it from the same episode, then there is an issue, because if you take the SI and SI plus 1 from the same episode, then they will be similar, right? Because if you're playing a game, the states are the same, or if you take it from the same episode. So what you have to do is you have to put it in a buffer, and you have to randomly sample from the buffer. So what I'm saying is that there are two problems. One problem is that this is sparse and delayed, and Q learning doesn't solve that, and it's a problem that we have to solve using hyperparameter search and something. But the other problem is that when you sample episodes and take it from directly from an episode, then the state values are very similar. So if the state values are very similar, data is correlated, and if you have that, then basically in your deep learning, in your updates, this part is mostly 0, and this part, the SI plus 1, this part, the SI is similar to the SI here, and so it is very likely that the values are going to be similar for a certain action. So it may not learn over time. So that is the issue of the buffer. So to solve that, they say that let's consider a replay buffer, in which whenever we play an instance or play an episode, we just put it in the buffer, and then we take it randomly. We take these kinds of tuples over time randomly, and that's how we can solve the problem of correlated samples. So any issue in the replay buffer example? Okay. So last thing from this paper is that how do we play the episode, because we can we cannot start with an empty table and assume that everything will fall into place, because problem is that if you start with an empty table, like, and use this rule, you still have to play the game, right? Because the gameplay depends on the q values. So what we are doing every time is we're passing the state, we're taking the best q value, because that is the highest reward, and that's the greedy action, right? Because there's two ways to do it. There's greedy actions, and then there is a random action. So what they do is they propose a mix of the two. They say that we can forward pass this thing, and this becomes a greedy action, but then we choose something like epsilon greedy. So what epsilon greedy means, that in practice, when the network hasn't learned what to do, then let's say in the initial 20 to 30% of the steps of learning, it makes sense to uniformly choose an action with probability epsilon. Like, we randomly choose an action. Basically, we take a number. If that number is less than the epsilon, we'll play the random action. Otherwise, we'll play the greedy action. So we'll decrease this over time, and over time what is happening is that the greedy action is being played more, and the random action is being played less and less, and after a certain time we just fix it to a value. So this is a technique which is very common in bandit problems and reinforcement learning. And then basically using this, if they handle the learning part, and then eventually this is the final algorithm that they give. So I think it is almost 12, but I'll take my maybe 5 or 10 minutes more. People who want to stick by can stick. uh, but this is the entire algorithm. So you start with a replay memory, uh, and you initialize the action value with random weights, and then basically you play the episode. How do you play the episode? You take the with probability epsilon, you select a random action, and otherwise you select a different, otherwise select the greedy action, and then you execute the action in the emulator and observe the reward in the next state. And then you store the transition in the replay buffer, and then you sample it and train on it using the yj, which is the target using the Bellman equation, and mean square error. So that's the entire algorithm. So anybody has any question in this part? Like, I'll give you a minute to sift over it. So people may be asking, what is this phi? It's just the encoding. So they're taking the state and then they're creating a vector of a vector, like encoding the input. So this is not clear what encoding means, but in deep learning, you have an encoder and a decoder usually. So encoder reduces the dimensionality of the image, and that's what they're doing here. So if it's an 84 cross 84 image, then they're reducing it to say 20 values, real values. So that's what the encoding is doing here. Okay, any other questions here? Any questions here? Okay. Okay, so I'll move on to the final thing, which is the uh, game. So like basically what I'm going to tell you is that there is this website you should always go to. There's this called gym.openai.com, and it's a framework and toolkit for developing reinforcement learning algorithms. And what it supports teaching agents everything from walking to playing games. Like, there's an environment for every one of these, and I'll show you an example of what I did, and I'll give you the code for it. And then what the homework will be is that for $25, can you play it on one of these games and learn? You are allowed to use any technique, like there's no requirement on that. But basically, I showed you that there's this game called Card Pull, in which the goal is to balance the card pull, right? And this is a game with discrete actions, four-dimensional continuous state, maximum time steps of play are 200, and for every step you survive, you get a reward of 1. So if you survive the entire 200 steps, you get a reward of 200. And that's what I coded up. So I'll give you that code. And then this is a description of what the card pull is. It says that 15 degrees from, like, if the angle from the vertical position to 15 degrees left or right. If it falls beyond that, that means the game is over. That's what it's saying. And then in the paper, they have like 7 games or 8 games that they try on. Uh, but this is the homework. And basically, can you take any game that they played and using my code, can you make it to work on any of these games? So anybody who can do it first will get $25. If you don't do it, then we'll accumulate it over the next assignment, and person who tries the most can also get it. It's okay. um, so get Q learning to work with any AI environment. What needs to be done is you need to change the network that I gave you and train, and you try different combinations of it. And the environments that I'm recommending are Pong, Breakout, and Space Invaders, because these are the cool games in the bunch. So Pong, Breakout, and Space Invaders are already here. In Pong is score is 20. So I'm not saying you should get a score of 20, but you should definitely not get a score of random, like minus 19 or minus 17. So try to get somewhere positive, something good that you can show me. Anybody who can show me first will get that prize. I mean, yeah. If there's any question on this, I'll give you the starter code. So for starter code, you can just note down this address. It's my repository. So it's, but I'll first show you what the code does. So this is free play. Basically, the game I played it without any learned agent, um, and this is, as you can see, like, I'm gonna start it. Wait a second. As you can see, like it's wobbly, it's very wobbly. It's not wobbly. What's happening is that the frame rate is very high and it's moving so fast, but basically it's terminating its episode very quickly, and it's moving, the branches are like uh, moving, the pole is moving very fast between the sides, and therefore the episode is not terminating properly. It's a random agent. And then there is a card pole agent that I got to work. So I'll show you. No, not this one, the other one. Yeah. So it will first train. So I don't know if you can see the size, but basically I'm going to run the code, and the code is pretty simple. It's showing you the reward, cumulative reward over 25 episodes, and you can see that this part is increasing. It goes to 200, uh, goes to approximately 200, about 200. And then it runs test episodes, 10 test episodes, and you can see that each of them covers 200. So you can see that it's not wobbly, so it's able to do it properly. So that means every 200 it goes. And then I can show you the training episode, training curve. The training curve goes like this. It starts slow, but it goes up over time, and therefore we know that this is training properly. So I'll show you the code for this quickly and briefly. Like, it will take me 2-3 minutes to go over the code because it's really well commented. So if you want to note this down, like, take this link, bit.ly, the rl dash code, and I'll just go to that. Yeah, so it's just this file, 1dqn.py, and it's just, I have instantiated the constants here, commented out what these constants mean. This is the environment being created. This is the replay buffer, which can just take some things and sample. We can sample from it. This is the network we have. So it's a deep network which input size 4. You have to modify this network to play with Atari. You have to modify it, introduce some convolutional layers here. Um, and the action space is size 2. So there's 2 actions, left or right, in cardboard, but you have to make it 6 for Atari. And then this is a policy you can see is like, if this is the epsilon greedy policy, this is the greedy part, and this is the random part. And then we decrease the value of epsilon. If you remember, like, epsilon was being decreased and it was maintained at a value. And then this is the training part. We have, this is a training loop. Basically, you take the Q values, Q essay for every essay in the mini batch. Then the second part of the Y. So if, like, this is the Y, the targets, and then there's a loss function, targets minus Q values. And then I play 25 I train episodes for 300 times, 300 episodes. And then after training finished, I plot the reward, and then I just show you 10 episodes of tests. So that's the entire code. So anybody has any question in the code so far? Because it's pretty simple to know. I know that you might ask what gather is doing here, what view is doing here, but this is just the simplest implementation that I could do. But if you just look at the PyTorch documentation, you will know what gather does, what max does, and we can do it in the next time. But so we have, like, I'll give you 2 weeks. We have 2 weeks because I'll we'll have the PyTorch one next time. So anybody has any questions? I can't. I have to stop sharing my screen, and then I'll ask you to raise your hands. Okay, now I can see your hands. So anybody has any questions, they can raise their hands. Any logistic questions, like what are we doing next time? We are doing PyTorch next time. So I'll tell you how to go through the code, like how the code works in PyTorch, and then you can attempt this if you want. Any general comments you guys have? Okay. So I think that's pretty much it for today. We'll have this session regularly every Saturday. And if you have any comments, you can always reach me on Facebook. So you can just search my name and or you can just ask the UW Data Science Club Facebook page, and they can direct you to me. But if you have any questions regarding like, if you do you guys want the slides? Do you want the slides? Then you can raise your hands. I'll convert it to
Yeah,
PDF.
I think we should post the slides maybe on the event page or on
Okay.
Discord.
I'll give you a PDF of the slides because there's a video embedded in it. So I'll have to delete the video and then create a slide. I'll give it to Jackie, and he will distribute it on the discussion, in the discussion part of the page then, right? So
Yeah, I
Jackie,
can do that.
yeah, you can post it.
Sure.
Okay. Yeah. Any other questions at this time? Just feel free to unmute yourself. Like, I'll be here 5 minutes. So anything you felt that could be addressed better, or that you didn't understand from it, you're free to leave if you want to. Don't worry about it. Okay.
I just want to say thanks for the presentation. It really helps.
Okay. Yeah. So this is gonna be every week. So feel free to come by next time as well. Next time we'll discuss PyTorch, but after that we'll have the A3C, and we'll go into other deep reinforcement learning techniques.
All right.
Okay. I see people saying thank you. Thank you. Okay. Anybody else? No?
Guess not. All right.
All right.
Good work. I think it was a good talk.
Yeah.
Good slides.
Yeah. So I'll just stop recording then.
Yeah, you can do that.